Hey guys, glad to see you at this lovely coffee shop for our meeting.
It's been so long. Remember that lab we were supposed to do during the coronavirus pandemic of spring 2020?
Yeah, that lab was really relevant. We really learned a lot. All these years later, and I've thought about that lab at least 4 times since.
What's the scoop for our agenda today? Hey Markus, the barista, can you make us our usual? Thanks.
Okay.
Woo, glad I can now discuss some caffeine in my system. We got aluminum 2024 on the horizon.
You mean with those hardening mechanisms? An aircraft application? I know that one.
Yeah, with low density, high strength, toughness, fatigue resistance, and corrosion resistance, what more could you want? It's a great alloy for sure.
What's the composition of this alloy?
Good thing you asked. I have it right here on my tablet to show you all.
Wait a second. What's the point of this meeting? What are we looking at with this alloy?
We're looking at the same process we've done since we last met. Aging.
Can we get a refresher on aging? I'm a little rusty. It's been a while since that MEMS 1011 class.
Aging is the last step of precipitation hardening, which is a process to strengthen alloys such as aluminum. First, we have to homogenize the structure by holding it at the single phase region for an hour. Then we quench to get the supersaturated solution.
The supersaturated solution is unstable, and a second phase will want to form. The precipitation of this second phase is called aging.
Right, the aging process is when finely dispersed precipitate is produced. This is through coherent precipitate strengthening and incoherent precipitate strengthening. I remember we learned that strength is a function of aging time and temperature. Peak aging and overaging, correct?
Yup, peak aging is when there's a maximum precipitation hardening and correlated strength. This has the best combination of precipitate size, amount, and distribution to impede dislocation motion.
And overaging occurs when the precipitates coarsen and space between precipitates is increased, which will reduce strength.
Oh yeah, it's all coming together. From ages ago. What are the different ways we can age?
It's like my iced coffee, natural aging, versus your hot coffee, artificial aging. You can age all natural at room temperature or artificially at an elevated temperature.
What methods could we use to analyze natural and artificial aging?
Hardness testing, differential scanning calorimetry, conductivity, and microscopy can all be used to find the peak aging criteria. However, hardness is the most effective way, since it's the quickest and easiest method to use on the sample. A few indents, bada bing, bada boom, and you're good.
Sounds like a good plan. What samples do we use again?
How about 28 samples with dimensions of 0.5 inch by 1 inch by 0.3 inch, with 7 samples at each temperature. The aging temperatures will be 20 degrees Celsius, 170 degrees Celsius, 190 degrees Celsius, and 240 degrees Celsius.
But first, samples are fully solution annealed for 1 hour at 495 degrees Celsius.
Can't forget that. What are the holding times?
I have this nifty resource that can show us holding times for the temperatures we're using. Previous research shows quicker aging occurs at higher temperatures.
Sweet! We can test using Rockwell B hardness with a minor load of 10 kg force, major load of 100 kg force, and a dwell time of 5 seconds using a ball indenter.
Let's do 10 hardness measurements distributed throughout the central region of each sample. This should give us a good statistical significance. We just have to make sure that the distance between locations is greater than 2.5 times the diameter of the indent. This should avoid inaccurate data from work hardening.
Good game plan. Let's meet back at this coffee shop with results.
Welcome back, folks.
Hello, we are back.
Ah yes, look at these great results. No discrepancies in our data.
Wow, you can clearly see the peak aging time for 170 degrees Celsius is 48 hours, 190 degrees Celsius is 12 hours, and 240 degrees Celsius is 15 minutes. For the artificial aging, the hardness increases to the maximum hardness and decreases afterward.
Natural aging shows a hardness increase and a plateau after 100 hours.
So, the trend we're seeing is that artificial aging shows a maximum hardness at peak aging, and the greater the temperature, the lower the required holding time. With natural aging, it takes much more holding time, and the hardness value reaches a maximum.
Wow, just like the good old days with that aluminum 2024 lab report.
Good thing we learned this material back in the day. Look at us now. Markus will be proud of us.
I can't wait to actually test out this aluminum 2024.
Me neither.
Cheers to that.